So far in our quest to reach, F equals ma, right? F equals ma. We just figured out what we're going to use for force. We're going to use torque, right? So this guy is Rf sine theta, right? We can't just use mass, and I'll show you why, right? So we got to figure this out, and that's what I'm going to show you right now. Okay, we can't just use mass, and that's because the geometry matters. Okay, so let's just hit the right arrow here, and this is a very nice demonstration. I've got a couple masses. Actually, I've got a couple C clamps, and I clamp them at the end of like a meter stick, and then I've got a couple, and I clamp them on either side of my hand. This one is very easy to twist. I can twist it like this, and it's very easy. And of course, the reason it's easy is that when I'm accelerating it, these guys only go in a little bitty circle, whereas these guys, if I twist it, are going in a huge circle. They've got much farther to go. So even if they have the same mass, this one's super easy to twist, and this one is very hard. Okay. In fact, it's like 1, 2, 3, 4, 5 times farther. It's actually 25 times the moment of inertia. So let me show you why it depends on the square of r here. Okay. Okay. So here, let me just show you this. Let's suppose that we've got some mass here, okay, that's at some distance from the center, okay? And I want to make something where I can just substitute in and get torque is I alpha, okay? Well, let me show you what I've got to put in there. Okay, so first off, let's exert a force on this thing, right? Okay, and I think we would all agree that if I exert a force on this thing tangentially, right, this mass would move tangentially, and Newton's second law would still apply, only it would go in a circle, right? So I think we can agree that we'd have F equals ma tangentially going on, right? Okay, this rod would exert a force to the center, but it would always be at right angles to that force, and so therefore it wouldn't change that acceleration, okay? Now, I know that I want there to be torque on the left side, but now I've got force. So what I'm going to do is I'm going to multiply both sides by r, and I hope you're okay with that. I'm going to multiply this side, and this side looks fine with an r on it, but I'm afraid if I put an r here that I will mar this side. I will mar. Okay. All right, there we go. That's my big joke. Okay. So let's see. And then I want to have alpha on the right side. So the way to get alpha in there is, remember, A is alpha r. Yeah? So I can just make that substitution. This is a tangential relationship, right? Okay, so I'm going to substitute alpha r in for that. And now I've got Rf, which is torque, right, is m alpha r times r, right, which is mr squared times alpha, right? So now I've got torque. This side, this is torque, right, is mr squared times alpha. So the thing that is I, if the expression is torque is I alpha, it must be that I for this thing is mr squared. And indeed, most moments of inertia look like that. There's a mass and a radius squared, okay? Except it gets a little more tricky than that, and that's because not all masses are these little concentrated point masses at the end of a stick. Sometimes they're spread out, and we got to deal with that, and we have to use calculus. But you don't have to use calculus. It's already pre-used for you, okay? So, for example, if we have a cylinder, some parts are close to the axis, some parts are farther away. It's going to animate both things. Okay, isn't that funny? It's like chunking on me for the animation. So some parts are far away. In general, what we do, and you would need calculus to prove this, okay, is that for this case, for a cylinder, if you actually had a cylinder, this is the exact solution. If you have a homogeneous cylinder that doesn't have any voids or anything in it, right, this is it. And you can derive this with calculus. And maybe I'll put up a video where I show you how to derive it. It's a fairly simple derivation. It's one of the ones I can do. I'm not sure I can do like the sphere or something like that, but I can definitely. I've still got cylinder in me, you know. Okay. But anyway, that's it, right? And then if you look at a list of them, and I think I got this out of my old textbook, they always give you an axis of rotation. That's important. So if you rotate it about an axis this way, you could do that, right? It's 1/2 mr squared. If you do it this way, it's mr squared. This is your cylinder, so that's one of your main ones, mr squared. And then, if it's an annular cylinder, that is, it's got a void in the middle, a cylindrical void in the middle of it, you just go 1/2 mr squared plus 1/2 mr squared. Shouldn't it be minus? Seems like it should be minus. Plus mr squared. I think that's got to be a minus. Seems like it should be, right? All right, I've never noticed that. I've never really looked at that. I was assumed they had that right. And then this is, and it would be R1 squared or R2 squared minus R1 squared. All right, and then this is a sphere. This is a hollow wall, a thin-walled sphere, like a ping pong ball, right? Okay, a rod. Sometimes we'll accelerate a rod around the end of it, right? This is like a ski pole. You're holding onto this end and you're moving it like that, right? These are the main ones, though, really. This guy, this guy, this guy, as we see in the thing, right? Okay, so these are the big ones, right? We tend to use these guys over and over again. But, that's just because they will also roll down hills and stuff like that. Okay. Okay, so let's do an example here. Are you guys ready for this? Okay, 340. These are precision children, right? 40 kilogram children are sitting at 1.2 meters from the center of a merry-go-round that happens to be a uniform cylinder. These poor kids, they don't have any better toys to play with, right? So here's this cylinder, this uniform cylinder. Ooh, that's almost good art, right? And these kids are playing out there. Like, ooh, all we have is this cylinder to play on. We got the center of rotation. Okay. Other kids have nice toys, but we just have this stupid cylinder. All right. So basically, the moment of inertia of this whole system is going to be the moment of inertia of the merry-go-round plus the kids, right? So I is going to be 1/2 mr squared, right, for the cylindrical merry-go-round, right? And then it's going to be 3. And then if they just give you an object at some distance, just pretend it's a point mass, that it's mr squared, like this. So the moment of inertia will be 1/2 240 is the mass of the merry-go-round, and then its radius is 1.5. And then 3 children, right? 3 precision 40 kilogram children, right? Times, they are only 1.2 meters from the center. All right, let's calculate this. 0.5 times 240 times 1.5 squared plus 3 of these guys times 40 times 1.2 squared, 442.8. Kilogram meters squared. We only have 2 sig figs, so we'd have to say about 440. Ta-da. Alrighty.